As you have noticed by now, Günther Rüdiger can't come, unfortunately, so we'll start with Kuhn Krümmer and the negative magnetic pressure effect in stratified turbulence.
Thank you. So, yes, I will start talking about turbulence on magnetic concentration. This is work I did together with Axel, Nathan, and Nico here. First, to sketch the context. Yesterday, Professor Parker announced that there are a few problems left in solar physics. Sunbursts are a classical example of long-standing ignorance, well-known for centuries, fascinating physics, but still not understood from the basics of physics. So I will just give a brief outline why actually this is not understood from basic physics. I will give a few alternatives which people have come up with, and will then focus on how we are trying to solve the problem. The standard model for for generation of sunspots is you have a thin flux tube which rises from the bottom of the convection zone with very strong field strengths and then pops out of the surface. There are a few problems with that. First of all, will these tubes remain intact? This is not confirmed by simulations. For one, people add a certain amount of twist to tubes, but then this twist is not observed at the surface. Another question is, do they rise? Because, again, simulations have shown that tubes can as well be coming downwards. And finally, actually the most tricky question, do they even exist? Because nobody has actually produced very nice flux tubes yet. So we can try to go for an alternative. Instead of creating them at the bottom and transporting them all the way up, why don't we try to generate them at the top of the convection zone through a surface instability? So, a few tricks have been tried. Last year there was a paper by Differential et al. About LES simulation. Unfortunately, the physics was not fully clear, but they did get some sunspot-like structures. In mean field simulations, there were results by Pichatino from Azul in 2000, where they assumed a dependency of the plasma properties, in this case thermal diffusivity, on the magnetic field. And they again create something spot-like. Also, in this paper by Vandenberg, Leoren, and Lubachevsky, there was formation about sunspots through introducing the dependence of the physical stress tensor on the magnetic field. And this is the fact which I will elaborate on a bit. If you have turbulence, then at first you see that you will have a strongly diffusive transport mechanism. And this is associated with first order closure. And you will see effective transport coefficients appear. But on the other hand, turbulence can also have strongly non-diffusive effects, which originate from higher order closure. An example is inverse cascading. So, when we have turbulent pressure, this is for the isotropic case formula how it looks. It has been shown in this paper that turbulent energy is approximately conserved. And if you then subtract one formula from the other, you see that in the presence of magnetic fluctuations, you will have a reduced pressure. because of the presence of these fluctuations. And we try to simulate this in direct numerical simulations. This is a stratified box with an opposed magnetic field in the horizontal direction. And unfortunately, we do not see any structures yet. But we do see the effect which was predicted in the formula earlier. We get a reduced magnetic pressure, and we get even a net negative effect of applying a magnetic field. This is C direction, and if we actually not plot it just in the C direction over the solar radius, then we see that the curves collapse in a rather nice single dependence on magnetic fields divided by the partition field. And here we introduced the TP, which is mainly indicating the difference. Here. This is the difference between the mean momentum tensor in the absence and presence of magnetic field due to the fluctuations. So this was the formula which shows the reverse feedback. Of course, if we want to see what the effect is, then we have to compare the pressure in a spot with enhanced magnetic field and the area with no magnetic field around it. We have to look at the pressure difference. And you see that we generally have this negative feedback, but it can be reduced by presence of magnetic field which is already present without a mean field. Small scale, so-called small scale dynamo field. And we see this in our simulations because I forgot, these curves have all different Prandtl numbers, so for a very low Prandtl number, you will see that there's less, that this value will be less. If you go to higher Prandtl numbers for the same magnetic Reynolds number, there is more small-scale dynamo action and effect will become less. So the relevance of this work. So in mean field, we do see some instability appear. In DNS, we do not see it yet. Possible ways out of this is to go through parameter search, changing convention, boundary conditions, include more physics. But we shouldn't just focus on this model alone. Other than just putting in flux tubes, there are plenty of other manners to generate magnetic fields. And it was a very short talk.
Questions? We have a lot of time for discussions now.
Thank you very much. So, the sunspots have some well-defined, more or less well-defined scale, right? Mm-hmm. In this effect, I don't see how easily the effect can have a well-defined scale. Of course, it will have a gradient of pressure somewhere, not somewhere, clear where. But still, is there any, like in instabilities, some instabilities have maximum growth rate with a certain scale?
Well, as I already showed, we don't really see the effects yet in direct numerical simulations.
Yeah, so but before simulations, there was quite a lot of analytical work, right? So what's happened with the analytical work? Is there any well-defined scale associated with that?
Maybe I answer, you cannot see. Is it closer? First of all, typical scale, it is a scale length of density. It is typical scale. So if you take in solar context, say something scale of supergranulation, so it is, suppose it's that, it's more normal. And sure. The second is right, it was demonstrate both by analytically and numerically in previous work with Axel that it is a real scale of this magnetic ropes, more or less depth of density.
You talked about the problems with the standard model, but there is a reason why that standard model has emerged, because it can explain lots of the systematic properties of sunspots.
At the surface.
Yeah, at the surface. So given that lots of people have tried to work on generating sunspots at various different depths, and they've come to the conclusion that the best place to generate them is perhaps at the base of the convection zone or in the tachocline, because that's the best place to...
The best place is to store the magnetic field is at the tachocline.
Right. But the sunspots have to emerge with systematic properties that you see in sunspots. So I don't quite see how you're going to get those systematic properties just from an instability of a small-scale dynamo.
But it's not reasonable to extrapolate all the results from the surface. I mean, at the surface they're really nice, but how deep can you extrapolate?
The question is, where are the sunspots formed?
Yes, and I don't say I have an answer for that.
No.
But I'm answering that you shouldn't just focus on things that you don't really know that are there. It's in flux tubes.
But you shouldn't just focus on the surface because you can see the surface. I mean, that's a mistake of observers, I think. We shouldn't, as theoreticians, just because we can see the surface, make that a special place.
But is it be true there are no mechanisms to produce those flux tubes which supposed to raise through dozens of scale heights, right?
Well, I think the whole essence of flux tubes is perhaps the wrong way of describing it. There are mechanisms for producing concentrations of magnetic flux from layers at the base of the solar convection zone. There certainly are. In fact, this mechanism would work. It is just as good that, isn't it?
Yeah. In principle, of course, this is idealized situations. It's difficult to explain by this simple model some spots formation. But what is the good news? That it's possible to form strongly homogeneous magnetic field from initially homogeneous distribution. So this is the main difference between previous studies and these studies, where we started with the uniform distribution of large-scale magnetic field, and then it can result formation of strongly homogeneous. But we agree with you that it is far from the sunspot explanations. We need also to add additional layer for the spheric layer in order to give flux tubes to be going to be for the spheric layer.
But your mechanism for forming these concentrations works well wherever you have a gradient of turbulence, as I understand it. So it works well at the base of the solar convection zone. It doesn't have to work at the surface.
This one does only work at the surface.
Why?
Yeah, this mechanism works in just in the base, in the convective zone, but the best conditions for excitation of this instability, upper part of convective zone, not surface, of course, but where magnetic diffusion is less, turbulent magnetic diffusion is less, and also,
Alphinic velocity larger because
Yeah.
density is low.
So
It is some compromise.
I mean, the instability requires strong stratification, and the stratification in the deeper layers is less. That's why.
But other things are more in your favour. Okay, so the stratification is less, but there are other things that are more in your favour. Like the length of timescale you can store the field there to act on it with various things. It's better in the stably stratified light, right?
It may already be too long. This is one possible other worry. I mean, if you really think about magnetic electricity conservation, then the timescales may be far too long at the bottom of the convection zone. We don't know that yet very well. Another thing that is important to say is the instability is non-axisymmetric, or it's three-dimensional. So there is actually a short length scale in the direction of the mean magnetic field. so as to produce bipolar regions. So typically you produce bipolar regions from this mechanism. I think another thing that maybe Patrick would show when he has his talk is that the simulations of convective dynamo action that he has been producing with Marit show that as a dynamo runs into saturation, the magnetic field structure is far less from fibril as it used to be in the kinematic regime. Yeah. Whether it's the same sense of fibril, of the meaning of the word fibril, as Gene Parker mentioned in his talk, is another question. I would rather think that what Gene really means is segregation of magnetic field. But as far as the fibrillity of the field is concerned, one does see a lot of small-scale structure as long as the large-scale dynamo is not excited. And then at late times when the dynamo runs into nonlinear, in the nonlinear saturated regime, it produces a great deal of volume-filling magnetic fields that are no longer fibril. And nevertheless, if you actually do a cross-section of the magnetic field at the surface, you all of a sudden see rather small isolated structures. It's quite different. The surface cross-section looks very, very different from looking into the volume. So in that sense, I think one should be alarmed, or worried possibly. But I think I should say at the very least that there is this mechanism of magnetic pressure, or total turbulent effective pressure reduction, and its effects are not fully explored. I think it is worthwhile understanding what exactly is going on. And if it is a real effect, it ought to be seen in three-dimensional simulations eventually. And it's also not always clear that one does see these effects immediately. I remind you of the alpha effect dynamo. When was it first seen in simulations? The first simulations that have been done on helical MHD were in 82 by Uriel Fritsch, 81. And they did not, they said explicitly, helicity does not matter. So no effect from alpha, obviously. They found small-scale dynamo action, even if there is helicity. So there was no successful demonstration. 10 years later, 91, the same result. People involving KIDA, for example, did three-dimensional simulations. They said, in the literature, from the literature we know that helicity is good for the dynamo, and they saw no effect. And then another 10 years later, for the first time, when we did actually allow for sufficient scale separation, you saw for the first time this effect. So it took not only 40 years to find it, but actually 20 years of numerical simulations to find it eventually.
Thanks. You mentioned that there is observational evidence for the standard model, and I think you referred to the twist of the bipolar regions?
The tilt.
The tilt, and that can only be explained by deep-rooted flux tubes, or could that be...
No, I didn't say that. I just said it can. I didn't say it could only be explained. I just said if it's in a shallow layer, that's something that you have to explain. The systematic tilt. So
systematic tilt is basically a relaxation, right?
Systematic tilt needs to carry force. We haven't in our model. I think we should be not so serious in sense of that it's a real model of real active region. Of course not. What's demonstrating this work that is real dependence of magnetic field with negative part. And even in 35 turbulence, it's a main result of this study. What we say now it is just huge. It's not to me.
All right. Thanks to everyone who contributed to the discussion, and let's thank Kuhn again for his talk. Next speaker is Simon Candelaresi, and he's going to talk about magnetic helicity effect on the solar dynamo.
Can you hear me? Is it working? It's on. Oh yeah, it's on. Right. Okay. So I will talk about magnetic helicity and gauge issues with magnetic helicity. This talk is a bit technical, but I will give a quite physical motivation for it. So magnetic helicity is basically the this is the main topic of my PhD thesis, which I'm working on. So let's see. Yeah, there it is. So I'll give a quick physical motivation why we should be concerned about magnetic helicity. And I think Anwar this morning showed a very good introduction to magnetic helicity, also in the context of dynamo theory. So magnetic helicity density is simply defined as the dot product of magnetic field B and its vector potential A. And what you usually have in dynamos, well, how do you create a dynamo? You usually have turbulence, small scale kinetic motions, which is this omega dot u. It's both are small scale quantities. And this typically creates also small scale current helicity. And that also creates a small scale magnetic helicity with the small scale fields A and B. Now, why is this small scale magnetic helicity important? Well, it was found in 1992 that it works against the dynamo. And more specifically, it was found that the magnetic energy, which is stored in the large scale fields, is reduced with the magnetic Rayleigh sum like 1 over Rm. This is called catastrophic because if you go to astrophysical objects like galaxies and the sun, you will see the magnetic Rayleigh sum is extremely high, which is like 10 to the 9 for the sun and 10 to the 29 for galaxies. So this suggests that we should get rid of small scale magnetic helicity to successfully create a dynamo with strong magnetic fields, which have also length scales which are larger than the double length eddies. So now, for what I show here is some work which we did in 2009 with Axel and Piali. And there was a one-dimensional nuclear dynamo where the forcing came with kinetic helicity, where we injected kinetic helicity, and that's where the energy came from. And so we had two setups. In one setup, we had a wind, which was increasing linearly. So the midplane was 0, and the other topic was finite. And the other boundary was open, so magnetic helicity fluxes. So the idea was that this wind carries along the magnetic field and also carries along the small scale magnetic helicity, and small scale magnetic helicity can be shed and be removed out of the domain. So as a result, this was without wind you have this catastrophic quenching. So this is magnetic Rayleigh sum, and this is the magnetic energy which is stored in the large scale field. Now, without the wind, you have this catastrophic quenching here, but with the wind, it's alleviated. So this was not extremely surprising. But what we also did is we closed the boundaries. I mean, in this setup, we closed the upper and lower boundaries. But we allowed for diffusive magnetic helicity fluxes through the midplane. So the magnetic helicity could just switch to the other hemisphere, if you like. And so without the diffusive flux, of course, there's catastrophic quenching, but with the diffusive flux, you can alleviate the quenching, which saves your dynamo. So now this was the physical motivation, why we should be concerned about magnetic helicity. And what we did in a subsequent work is we were looking at its gauge dependence. So magnetic helicity is of course gauge dependent, and also magnetic helicity fluxes are gauge dependent. So how does this influence the physics? Well, it shouldn't influence the physics at the end. So, and what we did here, we considered a quite special gauge, which we call a vector resistive. Now, why is it called a vector resistive? So you've got the induction equation with the magnetic field and the current density, and you can simply uncurl this induction equation, and you get evolution equation for the vector potential. And this one is a resistive gauge because you have this resistive term here. And you can also uncurl it to the vector resistive gauge. So we also have the same resistive term here and an advective term here. Now, due to this advective term, you would expect different magnetic helicity transport. And at the end, you would also expect that the magnetic helicity is stored in different scales. So this is what we wanted to see. Now, right. So now we simply solve for the MHD equations in this vector resistive gauge. And well, just show you the three equations which you solve for. And so AR, simply denotes that vector potential is in the vector resistive gauge. And well, if you do simulations, you see that all the simulations crash, which was a bit of a downer, I would say. But we just did a workaround. So instead of doing the simulation with a vector resistive gauge here, we simply do them in the resistive gauge and just make a gauge transformation with the gauge field lambda, which simply transforms from the resistive gauge to the vector resistive gauge. And then we compute all our gauge-dependent quantities in the vector resistive gauge by applying this gauge transformation. Of course, lambda has also to obey evolution equation. And now, right, so this is a plot of the root mean square value of the magnetic helicity normalized to the total magnetic energy. And the red one is a computation in the direct gauge, so when we really had this vector resistive gauge, and of course after some time see the simulation crashes. While applying this method I showed you before, which we call the lambda method, which is the blue line, it just runs through. So now, why is this unstable? So if you look at the evolution equation for the magnetic vector potential, you see that there are terms, curl, gradients of this of lambda. Now, of course, this has to be zero analytically, but numerically it's not. And this is why we get some spurious contributions to the electric current density. So, and that's also adds up some spurious contributions to the Lorentz force and adds up some additional motions, and this eventually leads to the crash. Now, this is also shown here in these diagrams. So, this is K, the length, inverse length scale, and this is a power spectrum. And as you can see, you build up, this is in the vector resistive gauge, you build up velocities, which are small scale velocities, and they act back to the wider Lorentz force on the magnetic field, and also on the vector condition. Yeah, this is a snapshot shortly before the crash. Okay, now so far to the London. I think I should skip this slide. This is not much more important. So now let's go back to what we actually wanted to see. So we wanted to see how helicity transport is affected by the gauge. So what we did here is we compared the transport of the helicity with the passive scalar. So we not only solved the energy equations, but we also solved the equation for the passive scalar C. And if you have a look at the time evolution equation of the magnetic helicity in your vector resistive gauge, which is here, and you have the resistive terms here and then some flux terms here. So if you are in a kinematic regime, that means the Lorentz force is negligible. And if you go to high magnetic Reynolds numbers, then you can see that the evolution equation for the magnetic helicity and the vector resistive gauge, it's the same as the evolution equation for the passive scalar. So I would expect that both behave in a very similar way. Now, this I plot here in this diagram, so you have the length scale, the inverse length K in the power spectrum. And for large length scales, the passive scalar C and the magnetic helicity and the vector resistive gauge show very similar behavior. So here, this is a power law of like 3/2. And at higher Ks, you also see a very similar power law. Now, for the resistive gauge, well, this is different. You've got a power law of 2, and here you see also a difference in the power law. Now, this is different in the saturated regime, so where the Lorentz force actually plays a role. So there you can see that the resistive gauge shows a very similar spectrum as the passive scalar, while the vector resistive and magnetic helicity in the vector resistive gauge shows this tail here at high Ks. And this we simply attribute to the possibility of this gauge to transport magnetic helicity to the length scales of the small scale turbulent eddies. This is why we get contributions in high K. Okay. Now conclusions. Well, I showed that we can apply the lambda methods to compute gauge-dependent quantities in a gauge which is numerically not stable. And I also showed that the vector resistive gauge is able to transport magnetic helicity to small length scales. And well, that's it, thanks.
Questions, please.
Can you tell us if there is some conditions on your vector potential that you can have your self-induction equation gauge invariant? The self-induction equation is gauge invariant, right? This is the question.
The induction equation with the vector potential.
Yeah,
that's gauge dependent.
It's gauge invariant.
This one.
No, gauge invariant. It's not gauge dependent. I'm asking for gauge invariance. Something different.
So
Maxwell's equations are gauge invariant. Right?
If you're writing for the vector potential, there's gauge dependence.
Yeah, actually, well, what changes, especially the flux tones. Yeah, of course. I mean, they are gauge dependent. I mean, this is a resistive gauge. You have this guy here, and you have the same here, but you have additional effective term here. So the equations are gauge dependent.
But when you perform the gauge transformation with the gradient of scale, right? This is a gauge transformation.
This one?
Yeah. Yes. Okay. So this is the condition. So you're gonna have a condition on the scalar, right? An equation for the scalar in order to be gauge invariant.
Yeah. Well,
This last one, yeah.
We have an evolution equation for this lambda. Yes.
Thank you.
Okay, Anwar, please.
Yeah. And with this evolution equation, you get results which are gauge invariant, correct? The final results, the conclusions.
Well, the conclusions, no, because we are looking at magnetic helicity transport, and that is gauge dependent.
Yeah, but it's again, it's a tool. Looking at transport of magnetic helicity is a tool. it's not an aim as such, right? You want to do this for some other purpose, to study some phenomenon.
Oh, well, the idea was to
first Nathan and then also.
Let me ask a question. You demonstrated in the beginning a level of saturation of magnetic field. And you give two examples. One with flux due to velocity, magnetic flux, and diffusive flux. Can you try with another coefficient, larger a little bit? Say 0.5.
You mean the magnitude of the
coefficient in second panel?
This one?
Yes.
Yeah, you can also have a lower diffusion.
Yeah, but it's in large scale model again, understand? Or you, what happened in explaining here? Maybe I don't understand.
Well, what you have here is, so you've got your domain, and you've got a midplane. And at the midplane you have a gradient of the magneticity. So now if you say that the flux depends on the gradient of the magneticity, you need a coefficient, and this is just this...
As a result of numerical simulation,
no, we oppose it.
So if you increase, definitely this level of saturation increase. So it is very small just because it's all 0.05. I know that it's 0.1, it will be much better.
Yeah, but the idea was simply to show that it can alleviate it, and already with this coefficient, it's able to alleviate. Of course, you can change the parameters to get to different results. And Anna this morning showed also that by changing the magnitude of the advection, which would be in this picture, you get also different results. And if you increase the wind too much, then you also don't get any dynamo simply because you lose all your magnetic energy with the magnetic field.
How would that coefficient compare rescale to the solar case? How would that compare to?
You mean the physical?
Yes.
Well, I have no idea. But, well, it's a good question, yeah. But I couldn't compare.
In answer to the last question, this is in units of the turbulent diffusivity. So you would expect it to be, theoretically speaking, of order unity, so that the diffusion coefficient on the helicity transport is the same as on as a turbulent transport of magnetic fields. But simulations showed so far, we have determined this now from this two different simulations, that this coefficient is always below unity. That it is, in those two cases, still bigger than the 0.05. But these are simulations of the last year. To answer Anwar's question, first of all, it is true that the small-scale magnetic helicity turns out to be gauge invariant under circumstances where you do have a large-scale dynamo action. That has to do with scale separation for the reasons that you explained. And that is connected with a paper that Kanaswamy Subramanian and myself wrote in 2006. It is also confirmed directly through simulations, but Simon has not shown this here. This is work with Alex Hubbard. Given that the small-scale magnetic helicity is gauge invariant, we can go into a gauge which is physically appealing and interesting and revealing. And so the advector-resistive gauge, or the advective gauge in particular, has the advantage that the transport of magnetic helicity is equivalent to the transport of passive scalar. So that means that the transport of magnetic helicity is really just an advection process and is only along the lines of, along the direction of U and never in the direction of B. And this excludes an important transport method that we thought is an important one, namely the Wishniak-Chow flux. So we all thought the Wishniak-Chow flux is very important, but that can't be true if the magnetic helicity is really just transported like a passive scalar. And so in that respect, I think this was an important contribution.
All right, we have to move on. Let's thank Simon again. The next talk is moved from yesterday, and that's Hidetomo Sawai effects of magnetic dissipation in a collapse of massive star.
Good afternoon. My name is Kemel+candelaresi+sawai from Master University. I'm working on quark supernovae, and today I'm talking about effects of magnetic dissipation in a quark supernovae. The same meaning of the quarks of massive star. Okay, this is the outline of my talk. Let's start from introduction. Quark supernova is an explosive phenomenon which occurs at the end of massive star's life. And its explosion energy is about 10 to the 51 L, and its energy source is gravitational energy. And it produces a neutron star or black hole as a byproduct of explosion. And during the explosion, heavy elements, more heavier than iron, is synthesized, which contributes to chemical evolution of the universe. And they are also considered to be sources of gravitational wave. So quark supernovae is important astrophysically and astronomically. However, the explosion mechanism of it is still unknown. The numerical simulations so far show that the explosion occurs due to cooling by neutrino or cooling by neutrino or photodissociation of heavy nuclei. So I said numerical simulations fails to reproduce explosion. However, there are some exceptions. If we consider extreme condition, for example, very strong magnetic field initially and rapid rotation initially. So in that case, explosion does occur, and this is called magnetized supernova. First studied by Grant and Wilson about 40 years ago. And this mechanism requires very strong magnetic field and rotation with like this value. Here, PNS stands for protoneutron star. And this strong magnetic field corresponds to magnetic glass magnetic field. And this is 2 or 3 orders of magnitude larger than ordinary radio pulses magnetic field. So, magnetic supernovae cannot be a mechanism of to produce cannot be a mechanism of normal supernova which produce ordinary radio pulses, but could be or may be a mechanism of a special supernova which produce magnetic. Okay. So in this context, magnetized supernova have been studied for several years now. Among them, Tom Thompson et al. Studied the effects of resistivity in magnetized supernova. So magnetized supernova is considered to be unstable to magnetorotational instability, and so turbulent viscosity and resistivity due to magnetorotational instability may exist. And so if dissipation of magnetic field due to resistivity is effective, this helps the explosion. This is their scenario. So actually, in their one-dimensional hydrodynamic simulations, they found that successful explosion occurs. However, their simulations are in one-dimensional and hydrodynamic. So this should be done by multi-dimensional MHD simulations. For example, in the simulations, only the energy conversion sequence of magnetic energy to thermal energy and then kinetic energy is considered. However, in reality and multi-dimensional magnetic MHD simulations, this sequence direct conversion of magnetic field to kinetic energy should be considered and can occur. So in this work, we carry out two-dimensional resistive emission simulations to study roles of resistivity in quark collapse supernovae. And we assume initially strong magnetic field and rapid rotation, and also turbulent resistivity due to magnetic rotational instability. So let me do the setups. For numerical code, I have developed two-dimensional resistive emission numerical code Yamasakura, named after Untitled Chapter. Yamasakura is time-explicit Eulerian code, and this uses finite difference method in conservative form, implementing high-resolution central scheme by Kuganok and Tadamore. And of course, this has passed various test problems. And what we have solved is following resistive energy equations. And projectile supernova is 15 solar mass star with 10 to the 13 centimeters radius. And numerical domain is central 4,000 kilometers core. And we solve only a quarter of meridian frame, where axis symmetry and equatorial symmetry is assumed. The grids are stellium cylindrical coordinate, and these are mesh numbers. And for initial conditions, magnetic field is assumed to be initially dipole like this. And initial ratio of magnetic energy to gravitational energy is 0.5. And rotation is assumed to be differential rotation profile of this. And with this, angular velocity is faster for the smaller radius. And initial rotation velocity, initial ratio of rotation velocity to rotation energy to gravitational energy is also 0.5%. And for electric resistivity, uniform resistivity is assumed. And we have computed three models. The first one is ideal models with no resistivity, and the other two is resistive models with different resistivity values. And for resistive models, magnetic Reynolds number is roughly these values. Okay. Now I'm going to the results. So first, I show you a movie of density contour, density color map, and velocity fields. And this is ideal model and the most resistive model. First, for fluxes, and then bounces, and the explosion along the rotation axis occurs. Yeah. And you can see that resistive model explodes slower, more slowly than the ideal model. So these figures are depicted at the same physical time, and the upper figures are the same as for a movie. And it is really thin that the resistive model explodes slowly. Okay. And the lower panel is the ratio of magnetic pressure to matter pressure. And you can see that the resistive model, in the resistive model, magnetic field is much weaker than ideal model. So from these figures, you may think that the resistive model explosion is weak, and this is true. This figure is for time evolution of explosion energy for each model. And this tells that the stronger the resistivity, the lower the explosion energy. So let's see what occurs. So this figure shows time evolution of each energy component in log plot for the ideal model with thick lines, and for resistive model, the most resistive model for thin lines. First, look at thick lines. So during collapse, the rotational energy increases and it reaches maximum value as a bounce. Then after the bounce, there's plenty of rotational energy. Rapid rotation winds the magnetic field and produces the toroidal component. And the toroidal magnetic field is amplified, and at the same time, rotational energy decreases almost monotonically. And this toroidal magnetic energy is converted into kinetic energy, which results in explosion. Okay. And on the other hand, for the resistive model, look at thin lines. The time evolution of before bounce is almost identical to the ideal model. But after the bounce, for example, the toroidal magnetic field amplification is much smaller than that of resistive model, than of ideal model. This is because field amplification by differential rotation is ineffective because of resistivity. So at the same time, the decrease of rotational energy is slow. So it seems that the resistive model explodes slowly because it cannot tap rotational energy effectively into explosion energy. Then you may think that if they have, when they have same remaining rotational energy, they have same explosion energy. But this statement is wrong. So this left figure shows the time evolution of explosion energy in the context of rotational energy. The evolutionary track is in this direction. So first, during the collapse, rotational energy increases and it reaches maximum value as a bounce and then decreases. And evaluated as the same remaining rotational energy, the explosion energy of resistive model is still weaker than that of ideal model. So what happens? So this figure, the right figure shows the reason. So this figure is for evolution of gravitational energy in terms of rotational energy. Now evolutionary track is in this direction, this part of time sequence. And so as the same remaining rotational energy, gravitational binding energy is much larger for resistive model. So this makes the explosion difficult for resistive model. So in other words, so resistive model has the same fuel, say rotational energy, same fuel as ideal models, which is to be converted into explosion energy. But they consume fuels slowly. And at later times, it requires more fuel to break up binding energy. So it's kind of waste of fuel. So this makes explosion difficult for the resistive model. And finally, let's see what accelerates the matrix. The left figure shows time evolution of acceleration due to each force component. So you can see that in both ideal and the most resistive model, the dominant driving force is pressure. But in ideal model, the magnetic force still plays some role, some substantial role. And this right figure shows the time evolution of the ratio of pressure force to magnetic force. And it is seen that in the most resistive model, its explosion is almost pressure driven. The magnetic force is one order of magnitude smaller than pressure force. So in the most resistive model, the scenario by Thompson is close to the scenario of Thompson. And on the other hand, the latter two models, in the other two models, the magnetic force fields have still some substantial force strength, and magnetic field also directly drives the explosion. And this is the summary of my talk. Thank you.
Questions, please.
So you were discussing actually the supernova explosion in your simulation, but I didn't see any reference to the neutrino component. They are extremely important because they have a transition between optically thick to optically thin region in some part of the star, and they are extremely efficient in losing the energy that you have.
Sorry?
And they are extremely efficient in losing energy, in carrying out energy out of the system. So, how realistic is your simulation without including this important contribution? That is my question.
You mean you question that I don't include the effect of neutrino cooling, right?
Yeah, neutrino cooling, yes. You should have solved the neutrino transfer equation.
Yeah, you're right. But okay, so that's important point. But actually, in my calculation, that's not so important because of time scale. And neutrino is important both in cooling and also heating. But as for heating, it's not important because it's the explosion of my simulation occurs much more time scale of neutrino heating. And for neutrino cooling, I don't include the effect of neutrino cooling, say cooling of neutrino, but but I implement the EOS by Shem. This is a nuclear equation of state. And this includes the energy loss by photodissociation of heavy nuclei. So, okay, so both neutrino cooling and photodissociation of nuclei takes the energy, but only including photodissociation of heavy nuclei is maybe enough in this situation. I can include neutrino cooling, but the result may not change so much.
Matthias?
Yeah, for understanding. So you have started with a pretty high magnetic field. So is it because you assumed that during the collapse of the core of the progenitor, the field there was simply amplified to that value? Is that true? And a second question. So as I understood, these pretty high values of the resistivity, they should be considered as turbulence, belonging to turbulent resistivity. So is it the only turbulence effect you have included in your equations? Because if you include something like that, the equation should really be mean field equations. And then one should wonder whether other terms, which usually don't occur in the original equations, need not to be included then.
Okay, so for first questions, you were asking about the origin of high magnetic field?
Yeah, these 10 to the 13 Gauss, where do they really come from?
Okay, it's based on observation. So from observation, this time observations of massive stars, and these O-type stars and B-type stars are known to be high magnetic field. They have high magnetic field like this. This means this magnetic field is as a proof of star radius.
It is already due to the collapse of the core of the progenitor. Otherwise, I wouldn't
No, this is the main Shika star.
No, I mean, it's 10 to the 13 Gauss. I would not understand.
Yeah. After
It's
sparks.
due to the collapse.
After sparks. And this is comparable to my estimation. So based on observation. And I don't understand your
So you
second
put in
question.
turbulent resistivity. So that's why your equations must be in field equations. And that's why the question need you to put in other effects. Have you done so?
Diamagnetic pumping, for example, you would wonder if in a case of strong density stratification you get a magnetic pumping of your field. I also had this question. This is, do you resolve the MRI? Do you get turbulence as an effect of MRI occurring in your simulations, or do you assume the ether?
Yeah. So it's just a first step. Maybe so you're right, and I should include that effect. But in this first step, I just put the resistivity of constant. This amount of value of resistivity is assumed is inferred from MRI tables.
Okay, thank you. Let's thank the speaker again, and then next talk is by Rainer Alt on what was used to know as the Taylor instability.
Is that okay?
Okay, can you hear me? Can you hear me without the microphone? This is really weird. Can't you hear me without the mic?
Sorry, I couldn't resist. That's what happens.
Okay, that's right. So, computer's working, microphone is working. I'm talking about the Taylor instability, as we heard something about by Frank, by Marcus, any other things. It's about the instability of magnetic fields, which are coupled with currents within the domain of interest. And then practically all these magnetic fields are unstable eventually when the magnetic field is high enough. This could be very high, but could also be relevant for a couple of astronomical applications. I'm only mentioning one possible application later on in my talk, otherwise I will just concentrate on the MHD phenomenon as such. I have talked about this, actually about most of this already in earlier talks, so I hope there are a few people who haven't heard it. What we will be using is a spherical code, a spectral code by Rainer Hollerbach. It is, so in this first thing, when I talk about the incompressible study, I'll talk about this code. It's a spherical shell, and it uses the simple MHD equations in that case. We're trying to reach relatively high Reynolds numbers to have something like stellar cases, like 20,000 here, which is of course still far away from the microscopic Reynolds number of a star, but still it's in the right direction. And we can also add, but I'm not talking about this here, we can also add temperature effects like a stabilizing stratification in a radiative zone of a star, which will be interesting for like AP stars or for the interior of the sun. Right, that's the initial conditions of this spherical shell. We assume a differential rotation, which is just constant omega on cylinders, just to get rid of any hydrodynamic flows going on. And the difference between the equator and pole is 30%, so a typical stellar value, one could say. And we also put in an initial poloidal magnetic field, which is actually fully confined in the sphere, but it really doesn't matter for the later evolution. And then you see how the differential rotation and the field wind up d phi here in the middle. Very nice. But that's only half the story, because you generate Lorentz forces, and the Lorentz force will diminish the differential rotation, which is measured here by some steepness parameter, and it actually approaches zero after some time as the Lorentz force acts more and more on the differential rotation.
So if you would have an axisymmetric simulation, you would see this, you would see the magnetic field being amplified up to a point where it has reduced the differential rotation, and then everything in the end is just a decay to 0 to nothing, because we don't have any imposed field, there's no imposed differential rotation, so there's no energy source in the system, it will just, everything will decay. So we're not interested in this late. It's too noisy? Too loud? Yes. Sorry about this. Is it better now? Okay. We're not interested in this late stage here because diffusivities and viscosities are of course very low in real stars, so this will take ages in a real system, but it takes of course a finite time in a simulation. So we're looking at this. And now we take the snapshots from this axisymmetric simulations and wonder whether they become unstable or not. And we do this in a linear analysis, and this is the stability lines here for a non-axisymmetric mode, which is, in that case, the most unstable mode is an m=1 mode for the Taylor instability. And that's the stability limit. If you would take a snapshot at this time, then you would see that the stability limit is way above your actual simulated result, so this remains stable in a 3D simulation. While if you're after here, the stability limit is lower, you would see an instability if you run it in a 3D simulation. That's what we will do later on. But just to see where to look for when you look for an instability in this system. That's about this time. You see that antisymmetric and symmetric solutions are roughly the same. And that's what's behind it, actually, that in another result here with a different setup, actually, so that's why it's not fully compatible, but it shows the principle is that differential rotation stabilizes the system because it tries to sort of smear out the non-axisymmetric mode, which is the unstable mode. So if there's differential rotation, your stability limit rises. If there's no differential rotation, the limit is much lower than for the differential rotation. So you could, in our system, you could look at this as a sort of time here, because we start with the differential rotation, which is diminished, and once it is small enough, the instability sets in. Right, so we will probably see the instability in a fully 3D simulation, and then we can also ask about dynamo effect from the instability. That has been a long story already. Has been proposed by Hank Sprout that it could be a closed dynamo loop, and there were simulations showing the effect, there were simulations not showing the effect. So that's not fully clear yet. In principle, as you see, this is a snapshot of a fully 3D nonlinear simulations of the instability after here, when I put in a perturbation here and I do the full system. Then the system evolves into something very complicated. You could think of that the average turbulent EMF is something finite, which could drive a dynamo in the sense of a mean field dynamo, which is probably the only possibility there is for such a dynamo. Since I don't have an energy source in the system, because I was looking actually at something else, at AP stars, I cannot drive a dynamo here. But I can see whether the mean field coefficients have some certain amount at some time after the instability sets in. So that's what has been done here with the test field method, which is nicely written down by Martin Schrenner and colleagues for the same geometry, so it was easy to implement. And what we find is it's actually an average over some time. The perturbation is put in at this time, it's in metal and diffusion times here, which is something like 10 rotations or something like this. And short time after that, after the instability has grown, I average the coefficients over another couple of rotations. So that's what we find for the three diagonal components of the alpha tensor. And you see a very strong effect at the axis, actually. This is not really an effect of the instability as we found, it's more an effect of the rotating inner sphere that you get on the tangent cylinder. You get always this effect, you always get kinetic helicity on this cylinder, even without any magnetic field, you get an effect here. What can be attributed to the instability is probably this positive alpha phi phi here in the northern hemisphere. If you ask for the amplitude of this, then you can say that this alpha phi phi here, as I've measured, is about 1% of the RMS velocity in the system, which is relatively weak. Right, then you can also ask what are the contributions from all the coefficients showing up, because you have not just alpha phi phi, you're adding up off-diagonal components, you're adding things proportional to gradients of B, and this is all the terms, so I've just taken the phi component of the turbulent EMF and reconstructed it from the coefficients, and you see that you have a stronger effect from the terms proportional to B, and only a weak effect from the other terms proportional to gradients of B, which possibly excludes any dramatic effect like the delta effect in here probably. It's only destructive, as you see, is negative. Right, and then there's a new experiment now. If we can go to compressible domain now, and that's what the title was about. But this is really a very first experiment. I didn't have time to work much on this, but I can show you what we did together with Patrick Kepele. We used the Spencer code, which can do a spherical wedge, and which simply means that you cannot go up to the pole for numerical reasons. But this is not so dramatic for the Taylor instability, because that is you have a B phi at some certain latitude, you want to study the instability. It's probably not very dramatic to have the poles not inside the domain. But what we do is we do go over the full azimuthal range. So we can see the M equal 1 mode coming on if it's there. As I said, latitude is somehow restricted, and radius is again a spherical shell very similar to the one we had in the incompressible case. And then we had to do some sort of things, because we wanted to generate the toroidal magnetic field, like I was generating this with the differential rotation. While in the original code I could just put it in as an initial condition, here this will produce all kinds of flows and stuff, and everything will be a mess, and you can't really see where the instability is. So we were putting a body force and forcing a differential rotation. We can do it either just a shear, like this, so you have plus and minus velocities over your radial range, or you can also add rotation by adding the Coriolis term there with an additional omega 0 to that. And then we actually found out, I can show you already how it looks. So this is the differential rotation you sort of enforce with your body force, and then you generate a B phi like this, which is the simplest thing we could have in order to study simply the instability of a B phi. But then what happens then, of course, with this differential rotation, because it's not Taylor-Troutman type, you generate strong meridional flows, and this will sweep your magnetic fields in the corners and somewhere, so it also looks nasty. And that's why we did the additional trick of also damping the meridional flow entirely. That is not so harmful, because we are looking at an M equal 1 mode, and we are damping here with the azimuthal average of the flow. So we are actually only killing the M equal 0 flows. And the M equal 1 will still evolve. And then we have a B, which is also a very, very simple thing. It's just a radial constant field. Don't try to imagine how it looks like. We just needed to wind up the B phi. So, and that's the stable case, when the magnetic field is not strong enough, even after a long time, so that should be 1.5 Alfvén times here. So with the given magnetic field, the Alfvén time is just take the radius and how long it takes for the Alfvén velocity. And it remains stable. Well, that's the unstable case, where the whole thing shows, and in this case, an antisymmetric configuration. Oh no, that's BR, so it's a symmetric mode coming up, that's B theta, that's B phi. It's a symmetric mode coming up in this case. The initial condition is just random noise in B, which is being amplified now by the instability. Right, and then we can also check if the stabilizing effect of rotation is still present, and also that is present, so we add the omega here, and we see the critical magnetic field strength going up. That's a little film showing how it looks. Just for entertainment, not really telling it much more than I showed already. So that's the B-phi, how it finds its configuration in the differential rotation, and then the noise at some point is roughly after 1 Alfvénic time is amplified into the unstable mode. Okay, maybe a few words about an astrophysical application, which is AP stars. So there are a couple of A stars, stars with radiative envelopes, large radiative envelopes, heavier than the Sun, which show strong magnetic fields around a kilogauss usually, or a few kilogauss. And they all look different. They all have quite irregular magnetic fields on their surfaces, as far as we can see them already by Zeeman Doppler imaging now. And the question is, people have been looking into this, whether they can find stable magnetic field configurations staying there for giga-years, because these magnetic fields don't seem to change much. And the question is, can't this be the result of an instability? Like you take the Taylor instability, you let it pop up, and it will produce something more or less random. And because the origin of the instability is gone then, the strong fields inside, the whole thing stays as such for a long time. And if you take the earlier nonlinear simulations, which I showed you in the incompressible case, you can really see on the surface you can relatively complicated fields. It's the M=1 mode with some nonlinear interactions, so it's not purely M=1. It's quite reminiscent of the real AP star fields. And then you can also ask about the field strength, and that is if you wind up strong fields inside, which is no problem with an initial differential rotation like 100 kilogauss, for example, and you find from the simulation that a few % of this field are showing up on the surface, then this is a 4 kilogauss field, which is the same as is observed. So this is not totally unrealistic, and could be an option for explaining AP star magnetism. Which would imply, of course, what are the A stars then, is the next question, which have no magnetic fields. Then it could actually be, because they are rotating more quicker, they could have the toroidal field inside still being stabilized by the rotation and not popping up, not showing any field on the surface, and appear to be non-magnetic stars, although they're not. But then the prediction would be, once they evolve into giants, they become bigger, they become slower, of course, because of conservation of angular momentum, and then the fields must pop up. So all A stars evolving into giants should be magnetic then. That would be the prediction. Anyway, that was just an astrophysical outlook. And so this is just more or less what I said. We have the results. Of course, we need to do more here. That wasn't really compressible in the sense of density stratification, because density was still constant. So we really need to go on with this. And I will have a colleague working on this. I hope to have him earlier, so that's why I'm a bit only with this test example. Oh, I should mention the conference we're holding in August, which is one of these famous Think Shop series in Potsdam, and it's about magnetic fields in stars and exoplanets, and that's the date. It's the end of August in Potsdam. That's the webpage. You can go there and register right now. Thanks, that's all I wanted to say.
Very nice poster. Questions, please.
So in your simulation, you basically cut the interior of the sphere, the cylindrical part in the interior of the sphere. You took out the axis.
Yes.
Now,
in the pencil code.
Yes, that is understandable. I just wanted to make this comment. If you read the original paper by Taylor, he points out that the most dangerous part of the instability is exactly near the axis, where the geometry is actually cylindrical. It's not even spherical.
If there is field. If you don't put field there, then nothing is
just by regularity.
But
just by regularity, then. So I'm a bit worried that you are missing the most important part of the instability.
Yeah, I know what you mean. But I mean that holds for if you place the same field at 80 degrees or at 20 degrees, that makes a difference. But if there's no field at the pole, then there's nothing that becomes unstable. That's what I would say. But we need to be careful. I mean, we had this constant v phi over latitude, which would go to the pole, and that.
I mean, my suggestion is, if it's possible, to have a solution which is regular, with v phi goes to 0 near the axis, because by regularity it must go to 0 at least as some linear power of the radius, and then look at the stability for that solution. That might be much more stronger and vigorous than what you are trying to discuss. That is a suggestion.
Yes, I fully agree. This was just the simplest thing to set up.
Of course.
But we need to find better initial situations for this, actually. Right.
Matthias.
Yeah, I wanted to ask the same, but okay. Then another question. You said you performed a linear stability analysis at the beginning, right? So what was the equilibrium for which this analysis was done? Because usually you need an equilibrium.
There was none, because you put in the field in an m=0 mode.
In what mode?
The background field is an m=0 field. So you study the stability of the m=1 mode. So you don't even compute the evolution of m=0, so you don't even care about it.
But you need to know how fast the background is evolving.
That's right, yeah.
Only if it is slow compared to the growth rate of the incident.
That's true, yeah. But it will be on a resistive scale, of course.
Is it? Is it true? Is it not an equilibrium? An equilibrium would evolve on the resistive scale, but if it is a non-equilibrium,
I see what I mean.
So
I don't think it matters, yeah.
Have you looked for the K dependence of the coefficients?
No, Axel was asking the same question on a previous conference. I didn't look at it. I mean, I took these linear fields from the test field method. So these should be, in that case, the only coefficients as far as I understood it. When you only want the B and the gradient B. Well, okay, it could be local things, yes.
The question is how good this reconstructs the EMF. If you say, I only want to know these, okay, but you need to know what everything is necessary.
I see. No, I haven't done this.
Okay, thanks.
More questions? Okay, not the case. Let's thank Rainer again. And it's a coffee break then, I guess. And let's reconvene at 4.
Lui ha avuto un sacco di problemi. Mattias praticamente ha detto fatto un culo così. Invece non si setup che abbiamo noi, questi problemi non ce li abbiamo, perché noi abbiamo la cosa esatta.
Perché metti il magnetico all'interno del dominio e c'è anche la parte centrale.
No, perché io bilancio la forza di Lorentz esattamente col gradiente di pressione. E quindi non ho il problema di fare come fa lui, che ha ammazzato i pezzi di circolazione meridiana che gli davano fastidio. E infatti ho detto, scusa, come fai a sapere che il background nel frattempo non si muove per i cazzi suoi? Minchia stai perdendo. diciamo, di fatto gli ho detto.
No, l'unica cosa...
Quindi in questa tappa noi questo problema non ce l'abbiamo. E abbiamo, come dicevi tu, il fatto che potremmo andare fino al centro.
Una cosa dobbiamo vedere, noi le interpretazioni lo bilanciamo però solo su R.
La soluzione esatta. Guarda, c'è la soluzione esatta. E tutto non dipende da Z. Per il momento non dipende da Z. È tutto bilanciato, la soluzione esatta, numericamente bilanciata. Abbiamo visto con Ax.
Quindi perfetto, molto visto grazie al fatto che c'hai quella soluzione che ti...
Tu hai detto che già grazie al fatto che c'è quella soluzione esplicita, perché con un'altra la attacchi. Quindi questi problemi non li abbiamo, è come uno studio molto più raffinato di quello che fanno loro.
No, si può dire anche il fatto che c'è quella corsione in effetti possibile.
Quella non si era modificata, una minchiata, però quella piccola cosa
magari non puoi mettere l'oscillazione al centro, però
no, poi li possiamo fare,
si fanno combinazioni,
non ti preoccupare che poi esatto, possiamo fare altre, cioè questo è il primo mattoncino, da questo possiamo fare pezzo dopo pezzo, possiamo fare una cosa veramente con i controlli. No, questa cosa qua che mi ha detto che lui sa tra un po' e poi io riparto a giugno, dipende da giugno e continua a a giugno abbiamo un bel setup che funziona e possiamo cominciare a scrivere il lavoro sicuro. Infatti lui mi ha detto dobbiamo trovare e capire quando l'elicità viene prodotta e quando non viene prodotta. Il setup che abbiamo noi è già diverso perché noi siamo compressibili, invece quello di loro che ha fatto che è per te incompressibile. E questa è una bella differenza. Noi abbiamo beta parametro beta uguale 1.
Pressure tensor there?
Questo è test fit, questo è la cosa che devo fare io, so cazzo di test fit.
How's the initial conditions in the mean field simulation? That's how much it is.
Just certified that mean field conditions are determined.
Now, why do you get a bipolar region then? I mean, that's quite peculiar then.
Well, we get not a single bipolar region. We get different structures. We get sort of alternating touching structures. So to speak, a chessboard pattern.
Checkboard pattern. Oh, okay, I see that would, and then the strongest two would sort of.
It's mean field, so there are definitely gaps.
It's what?
There are definitely gaps which should be filled by.
Oh yeah. What's the limitation of the DNS Reynolds numbers you obtain?
Well, Reynolds numbers are actually okay. We don't really know why it's not working. Nathan Lieber thought that maybe either this addition of photospheric layer on top of boundary condition would be a good idea, or well, the effect is also increased if you add convection, for example, although it would stay within the same magnitude order, I think.
Okay, and have you tried like seeding a DNS with something that you know would be an intermediate stage of the instability that you observe in the mean field model?
No, we just...
You know, if you sort of help it to get...
Seeding, right?
Well, it just would be the next step to...
No, we haven't tried that.
Yeah, it sort of is cheating. But very interesting stuff in any way.
das immer größer, je mehr sich das mit Strom nähert.
Ja, ja.
So. Und je smoother das ist, desto weniger größer ist es. Aber wie gesagt, die Stabilität ist noch eine andere Frage. Die besten Kandidaten für Stabilität sind sicher das Gemischte.
Ja, ja, klar. Also, die Totaler und die gehen natürlich auch nur stabil in einem Leiter, ne? Also in einem Fernsehkontaktor.
Ja, wieso perfekt?
Konstant kann man vielleicht auch machen, ja. Ich habe nur das bisschen mit dem Kontaktor. Das ist total stabil. Und wenn man ein Vakuum draußen macht, dann sehe ich schon.
Ja, was ist für eine Rotation?
Keine Rotation.
Ja. Eine Rotation ist doch keine stabil.
Das kann man noch stabilisieren durch Rotation. Ja.
Aber gut, wir haben ja Rotation. Das ist nicht so, dass es daran fehlt.
Ja.
Interessant übrigens, Redfeld hat lange Zeit bestritten, dass Rotation stabilisieren wird. Im Gegensatz zu seinen eigenen Ergebnissen. Er hat insbesondere bestritten, dass ein polyregales Feld durch Rotation stabilisiert wird. Ihr würdet jetzt sagen,
Ja, das haben wir gemacht.
wir haben es auch gemacht, das aber unser Ergebnis nicht behaupten. Ja, genau, das veröffentlicht ihr das nicht gekriegt. Die Möglichkeit ist es, dass der Rahmen ist. Roberts hat da auch nicht gearbeitet. Das sollte auch ein Foto gehabt. Der hat das angesehen. Aber
Allerdings erst nach der Weile. Also wenn wir da sozusagen die Grenzzahlen mit dabei ist, kann ich nachgucken. Das kann natürlich sein.
Moment, was ist jetzt?
Genau,
Random Number ist bezogen auf die Rotation.
Genau.
Also, das kann sehr gut sein. Das ging insbesondere um Atomsterne. Und der schnelle Rotation. Das kann nicht sein. Und der kam jeweils zu Ergebnis, dass so Risiko hat. Das müsste aber das müsste sehr viel. Also es ist ein bisschen schärfer. Es ist ein bisschen schärfer. Also es ist vielleicht ein Faktor 1,7 oder 2. Das ist Rotation ein bisschen schärfer.
Ja, ja. Das ist schon
Ja, ja, ja. Das ist echt ganz schwer. Das ist irgendwie